Hello everyone, this is Nikita. Welcome to the episode 62 of Microsoft Hour of Code, brought to you by Millionlights. Millionlights is a TV channel dedicated to improving skills of people and their employability. Now, let me tell you more about Microsoft Hour of Code. Microsoft Hour of Code is a series of lectures, courses and talks by experts who are going to discuss the latest Microsoft technologies, topics related to programming and industry forecast that are all focused on employability. Today, we are going to learn developing Microsoft SQL Server Databases. This course is basically for people pursuing computer science. This content has been created by our partner Microsoft, and today we have Malcom and Bolton from Microsoft with us. Our expert will take you through table indexes, stored procedures, and other database objects. Learn about techniques from designing indexes, managing transactions, and optimizing performance and concurrency, and get best tips and practices. These courses can help you earn at least 4 lakhs a year, and for those who are already working, experience strongly influences pay in this job. So you can definitely get an increment in your salary. Now let's move towards the course Developing Microsoft SQL Server Databases. The topic we covered in the previous episode is implementing tables and views. In this episode, we will be covering the remaining part of this topic and see demo on table variables and temporary tables and move forward with another topic, which is implementing indexes. So let's get started with implementing tables and views and see the demo.
So once again, over to your demo machine and let's take a look at these two things.
So for this example, I'm going to use a database called People. I'm going to create a temporary table called People, which has all of these columns in, so personal ID, first name, last name, date of birth, date of death, and sex. I'm going to populate the table by inserting into hash people, by selecting the top 250 rows, all of the columns from a normal table called People.
Okay.
I appreciate that the naming may be a little bit confusing here.
Okay.
But
just remember the hash one is the temporary one.
Yes, correct, yeah. So if I have a look at account star from hash people, I have 250 rows. Okay. So what I'm doing here is counting all of the rows within that table. Okay. I have 250 rows in hash people. Now if I disconnect this session, reconnect.
And just to be clear, that even though it's the same window, this is now a different session because we've closed and reopened the connection.
So this table name is invalid because we've disconnected and we've come back with a new session, and because it's scoped to a session, it only existed in the previous session. So I'm going to do the same thing with a table variable now. So in order to create a table variable, I'm going to declare a variable of a table type with the same definitions. So I'll do that, and then I'm going to insert the same code
basically,
and that failed, and that's because the table variable is scoped to a batch. And the batch is what I've highlighted and just executed.
I see. Okay.
So in order for this to work, I need to declare the variable and insert the rows. Oh.
Nope.
Oh, because I reconnected, I didn't reconnect in the context of the right database.
We're in a different database.
Insert, yeah. So now I've got those 250 rows inserted. And if I do a select, it will fail because it's scoped to the batch.
Okay.
So if I want to work on that table, I have to do everything I want within that single execution.
I see. Okay.
Okay. And if we have a look at the estimated execution plan, I may be jumping ahead a little bit here.
Yeah, estimated number of rows there.
Yeah. So we've got the estimated number of rows for the select.
And it's
is one.
Yeah. So
when in actual fact we know that there are 250 rows, and that may not be enough at this scale to cause the execution plan to be any different. But as I mentioned before, we've seen situations of hundreds of thousands of rows later on and causing this problem here.
Oh, okay, great. Thanks for that. Now, common table expressions. This is another way of effectively creating a table-like structure for me to work with.
Yeah.
Do you want to talk me through this?
So basically, a common table expression is a mechanism for defining a subquery that can be used elsewhere in a query. So for this example here, it's a bit like a view that's then referenced within the same code.
Okay.
So it can be referenced multiple times in the same query with just the one definition. So for this example here, this select statement that we have in the middle that's wrapped in that with CTE year is then referenced in the subsequent select statement, and then we would do the aggregations or the distinct and count within that.
So in effect, what I'm saying with that with statement is I want to define for temporary purposes a table-like structure that's named. I'm giving it a name that I can work with, and then I'm going to reference that throughout the rest of my code.
Subsequently going to use. And it's quite a useful construct to reduce the amount of lines that you would put in code. It's not really a performance enhancement. But where we get into recursion, that's where you can really get the performance enhancements for this.
So if I had a table that had, the classic example for recursions is employees who have managers who are also employees.
Exactly.
I can query through and build up a hierarchy, build up an org chart.
Exactly. And this is what's coming up in the demo actually.
Oh, well, there you go. And there you go. It supports recursion, and there's a demo. So let's go see the demo.
So I'm just going to use the T-SQL database again. We'll create this common table expression here that we saw on the previous slide. Let's run that. So what that's giving us is in this first definition, we're selecting the year from the order date column as order year and the customer ID from the orders table in the sales schema. And then in the second part, we're selecting the order year and we're doing a count of the distinct customer IDs from the CTE that we've defined up here.
Okay.
So what we're looking for is the number of distinct customers that placed orders within 2006, 2007, 2008.
Okay.
Okay.
So that's a fairly simple example.
Yes,
we talked
absolutely.
about recursion, I guess that's what we're going to say.
Yeah, so the next one coming up here is this recursive CTE, and this is where the performance benefits of CTEs come in. So what we're doing is creating this anchor query is what we call the start of the tree. So we're doing this select statement from the employees table where the employee ID equals 5. Then we have this union all, and what we're doing is going to recursively go through the CT that we've created based on the employee ID of 5, and then select out that root employee and then everybody that works for them.
So in this sense, just to be clear, we know that employee number 5 is the CEO or managing director
Correct,
of the top of the tree. So we start there and then we'll recursively go down each level of the management hierarchy.
Yeah, exactly. So if we did just the select all of the employees. What we're looking for here is employee ID 5, and then we'll recursively go through all of the employees that have a manager ID of 5, basically.
Okay.
Let's go ahead and run that. So a recursive CTE is definitely something that you should follow up with in terms of preparing for the exam and in general. Being aware of common table expressions in general, but a recursive CTE is really where you're going to get the performance benefits from setting this up.
So as my old teacher at school used to say, it would behoove you to learn a little bit more about this before sitting the exam.
Yes,
so
absolutely.
A little tip. All right,
Absolutely.
great. Let's switch across. I think we've got one more major topic to talk about on the slides.
Yeah. So partition tables is a really important area of SQL Server, and it was an easy decision to include partition tables in the context of this course because it's really a fundamental performance tuning area for within SQL Server. So this example, we have the sales, the orders table within the sales schema. We've got multiple file groups here, so we talked about file groups, we touched on file groups earlier on, and the idea here is that we are horizontally partitioning the orders table into multiple file groups to make managing a large table more efficient.
So to be clear here, I mean, previously we talked about creating a table and allocating it to a file group.
Yeah.
Here we're talking about creating a table and allocating different partitions within that table to different file
We're
groups.
effectively splitting a table across multiple file groups and probably multiple files as well to use it most effectively.
Okay.
So this is the idea where each partition would be stored in a specific file group. Indexes are automatically aligned, so this is a great exam tip here around indexes on partitions. A partition aligned indexed basically means if I created an index on the orders table, it would create indexes for each one of the partitions within the table.
Okay, so it partitions the index as well,
Correct.
In alignment with the table.
Yeah.
Right. Okay.
Yeah.
So okay, let's talk about how we would go about creating one of these things then.
Yeah, absolutely. So these are setting up the partition table. Again, from an exam tip perspective, you really need to understand this concept of a partition function. So this partition function defines the boundary values for partitions. So we would typically partition based on dates is a really good typical partitioning scenario, and this boundary values is basically defining, in this example we have here, so this is a date, so this is 1st of January 2000, so this first value that we have here, and we're basically saying anything that this is a boundary value, and between 1st of January 2000, 1st of January 2001, we're going to put them specifically into a partition. So we have in the code, a comment code there.
Yeah, I just want to call out that we've defined 3 boundary points, and if you think about this logically, if you make 3 cuts in something, you end up with 4 pieces.
Yes.
So what you do by defining 3 boundary points is you create 4 partitions.
Yes. Yeah. So we've got everything before 2000. We've got from 2000 to 2001, 2001 to 2002, and anything greater than 2002.
Okay.
As the partition function. And the next part that we would create is a partition scheme. So this effectively maps the file groups to partitions. So this is the next stage from the partition function and defines a file group for each one of the functions and the next file group that we're going to use.
Right, so we've initially created a partition function, 3 boundary points equals 4 partitions.
Yeah.
We've created a partition scheme, and we've specified 5 file groups because there's one for each of those partitions, and then there's one that says, hey, look, if I add some data to this and create a new boundary point, I want you to use this.
This is the next one that I'm going to use, yeah.
Gotcha.
And then when we create a partitioned table, so in this example, we're creating an orders table, we're creating it on the partition function.
Okay. So yes, as simple as that. The create table is create a table where previously we had on file group. It's now on the partition function.
Correct, yeah.
And we're specifying which of the columns in the table is the one that we compare to the boundary value.
Exactly, yeah.
Right, okay, great.
So partition function, partition schemes, definitely something that you'll need to be conversant with for the purpose of the exam.
All right, and I guess having spread the data across these multiple partitions, there's one or two cool things I can do to manage them. So why don't you talk us through that a little bit?
Yeah, absolutely. And again, definitely from an exam perspective, you need to be familiar with these the different ways you can manage the partitions. So the first one that we wanted to talk about is a split partition. So effectively what we're adding in is a new boundary to split a single partition into two partitions. So we're saying in this example here, we're creating so we're saying for a particular date range, we're going to cut it in the middle and we're going to separate those into two partitions.
So the classic example would be from previously, we had a table where the last partition contained all of the orders after the 1st of January 2002.
Yeah.
Now, if we kept that going for 13 months, we're then into 2003. So what we might want to do is insert a split that says, well,
exactly.
Keep the 2002 on one partition and start using the next one for 2003.
Exactly. So, and the next managing area is around merge partitions. So this is around removing a boundary to merge two partitions into a single partition. And you may do this for consolidation of archive data, of older data. So we have this sliding time window that you were mentioning there, where we've split the newer partitions. So we've now, we've split 2002, 2003 data. 2003 onwards is going on there. But if we look at the other end of this time spectrum, we may then want to merge, in this example here, this kind of pre-2000 orders with 2001 orders, for example.
Yeah, so perhaps I only really care about the most recent 3 years, and then everything else before that just gets lumped together.
Yeah, I still need it, but I'm not worried about optimizing the performance of it, because all of 90%, 99% of my work is at the front end of the table.
Okay, yeah, makes sense.
And finally, switch partitions. So switching partitions is a way for you to switch out. So we have this archive process that we mentioned that we would use maybe merge at the back end of the partition table, and we could use switch to actually switch a partition out of the table completely to put it into a different table structure. So in this example is exactly that, an archive staging table.
So switching at the old table. It's worth pointing out that $partition function, which is a way of finding out which of the partitions I want to switch. Here's the value, find whichever partition this value's in, and that's the one that I want to switch out.
Yeah, exactly.
Okay. So, for the final time in this module, you're up.
Perfect, right. So for this example, I'm going to, I'll drop DemoDB, because we've been using it previously. I'm just going to create a sample database here. I'm going to create a number of data files and file groups here. So a file group, I'm going to create a file group called FG0000, and then a file name associated with that file group. And I'm going to go through and create exactly the same thing for the other date ranges that I have in this table.
So there's nothing specific to partitioning here. This is just file groups we mentioned right at the very beginning of the module. If you haven't worked with file groups before, go and have a look at it. But all we're doing here is creating some file groups and adding files to them.
Exactly. So then the first thing I'm going to do is to create a partition function. So we've mentioned this before as the first thing to do, as range right values. So where I'm saying range right, I'm basically saying how would I deal with a value that was exactly the same as my...
So it's on the boundary.
Yeah, exactly. So if I had a value for the 1st of January 2000, I would store it in the right-hand partition rather than the left-hand partition.
Okay.
So I'm going to create a partition function called PF. Which has 3 partitions. I'm going to create a partition scheme called PS, which has 5 file groups in. which aligns to what I've created. Then I'm going to create this table on the partition scheme, which is on this date key, which gives me my partition table. So now I'm going to insert a few rows of varying values to distribute amongst these partitions.
Okay.
And if we have a look at this partition metadata script,
I guess perhaps just to point out, don't worry too much about the syntax. There's some deep diving into some system tables to find out what's on what's partitioned here,
exactly.
but the point is to look at the results and see how that data has been partitioned.
It's just for the purposes of demos, basically. So what we can see, if I scroll this up, it's showing us the partition scheme, the function, the partition number, and the number of rows in each partition. So based on the rows that we input, it's distributing them amongst partitions 2 and 3.
So yeah, based on the order date key, there have been 2 orders that were placed between 2000 and 2001 there. Yes.
Yeah, exactly.
Yeah, which matches well. Yeah, great.
Yeah, perfect. So this one was on the boundary, so
and it's ranged right, so it's gone into the second one.
Yeah, exactly. So the next thing we're going to do is this split. So what we're going to do is to split, because we've got our last partition is for
2002 onwards.
2002 onwards, yeah. So we're going to split that. Have a look at the partition metadata again. So we've now got a new partition in one of the file groups that we created in the beginning. So we defined all the file groups to begin with.
And it was specifically that last file group that we added when we created the partition scheme. We said, take the partitions from this function, put them on these file groups, and set aside this final one to be the next used one, and that's the one that's used. Yeah. Okay.
So the next one, we're going to merge ranges. So what we're going to do is to merge, so this partition here, partitions 1 and 2, because we're saying I'm not really interested in separating out data between 2000 and 2001. I just want it to be merged into history, basically.
Okay.
So that's what I'm going to do. And if we have a look at this partition scheme data again, we can see that that's been merged, and everything prior to 1st of January 2001 would now be in the first partition.
And the FG 2000 file group is no longer used in this partition table. It's freed up,
exactly.
Nothing on it. Yeah,
exactly. And then finally, I'm going to create a separate archive staging table, and I'm going to switch out all of this this 2000 data into the archive staging table.
So that's the table you just created. We've swapped the partition with that table across.
Exactly, yeah. Exactly. So if we have a look at the construct of the partition table again,
it's still there, but there's no rows in it.
Yeah, so we've moved those rows out to an archive table.
Okay. I guess just one final point to make about that. The reason we were able to switch between a partition and the table, they were both on the same file group.
Correct, yeah. So if we go back and have a look at that definition there.
Slightly before that, I think.
Yeah. It was specifically created on the file group there.
And again, without giving anything away, if you're preparing for the exam, be aware that if you are switching between a partition table and either another partition table or just a regular table, they have to be on the same file group for that switch to happen.
Yeah, absolutely. So partitioning, and again, it's difficult to do it justice in such a short session, but suffice to say that it's definitely an area that you should get some hands-on practice with and be familiar with these concepts of the order in which to set up partition table and also to manage it with switch and merge.
Fantastic. All right, let's close off and finish over on the slides. And it's been quite a long module. We spent some time at the beginning just introducing the whole course, and then we've covered a lot of ground here. We covered tables and some of the considerations for designing tables, thinking about your data types, your column names, all of that kind of good stuff. schemas and the idea that it's a naming boundary, and getting used to the idea of using that two-part naming approach when you're accessing your tables, or when you're working with tables, or any objects really. We talked about views. We talked about the idea of that being a kind of virtual table that is the metadata for that view is permanently stored as part of the database, so they're always available for you to query, and they provide an abstraction layer over the underlying tables. And then we compared temporary tables and table variables. Temporary tables exist in the tempdb database, and they are automatically deleted at the end of the session if they're local, or when the server is restarted, or the tempdb is reinitialized if they're global ones. Table variables we talked about, and I think the point you made there was they're great for small batches of data.
Yeah, absolutely.
If you start having table variables that have got huge numbers of rows, you might want to think about approaching that slightly differently. Common table expressions, a way of effectively inline defining a table structure and then using that repeatedly in your code. And one of the real benefits of CTEs was the fact that they're a great way to implement recursion. So you anchor the top level thing that you want to query in a CTE, and then you can recursively build out each level underneath that. And then finally, partition tables. And as you said, it's a really key component in optimizing the performance and the manageability of a SQL Server database, and a real key thing to prepare for the exam. So lots and lots of things that we've covered in this module. I hope you've found that useful. Go and give yourself a shake, have a cup of coffee, and make sure that you're comfortable with everything we've covered so far, and then come back and join us for the next module when we'll start looking at indexes. So welcome back. I hope you enjoyed your break. We're back now, having talked about tables and all things kind of tabular in the first module. In module 2, we're going to build on that knowledge, and we're going to talk a little bit about indexes. And I say we, but of course what I really mean is my partner in crime here, Christian. So Christian, what are we going to cover?
Great, thanks Graeme. So for this module, we're going to be looking at, first of all, clustered and non-clustered indexes. So the two kind of basic index structures that we have. We're going to look at covering indexes in the include course. So these are very important, both from your wider knowledge, but specifically for the exam. How you can obtain information about your indexes using dynamic management views. And we've got a few scripts and some specific DMVs that are useful to remember. We're going to talk about filtered indexes and how useful they are. We'll talk a little bit around statistics, which support a number of functions within SQL Server and the optimizer, but are very much aligned to index. And then we're going to talk about index maintenance as well. Okay,
so a lot of ground to cover. Let's move on and start looking at some fundamentals.
Let's get started. So in terms of fundamentals, so when SQL Server accesses data, so you do a select statement, very basic select statement, SQL Server will access the data based on a table scan or via an index. So in a table scan, SQL Server will read all of the pages because they're unordered, or they may be ordered, but SQL Server doesn't have any knowledge of the order of that data. And then when using an index, SQL Server will use the index pages to find the specific rows that it's looking for.
Okay, so I guess much like if you were reading a book, you could read it cover to cover,
yeah,
or you could look up what you want to find.
Yeah. And so indexes, we already mentioned in terms of the agenda, so indexes can be clustered or non-clustered, and it's really important fundamentals of working with SQL Server to understand the difference between clustered and non-clustered indexes. And you can create indexes directly with create index statements. Or, as we saw in the first module, when we're creating a table, if we specify a primary key, SQL Server will enforce that primary key by creating a clustered index. So mostly when we're working with clustered indexes, they're created as part of the definition of a primary key on the table.
Oh, okay, right.
So looking at a bit more detail around clustered indexes. So basically, the clustered index, the rows are stored in the order in which you specified in the clustered index. So they're stored in a very specific order, and because of that, you can only have one clustered index per table, because it really defines the order of the table itself, and it can't be ordered multiple ways. So when we create a clustered index, it's the table itself that we're referring to.
So there's one clustered index.
One clustered index. Right. So, and a table without a clustered index is what we call a heap. So it's a heap of data, it's unordered data. And while the heap itself isn't an index, understanding this term of a heap, a clustered index and a non-clustered index is a really important fundamental part of working with SQL Server.
So a heap might be if I had a bunch of bits of paper with, I don't know, documents with perhaps resumes for employees or something, and I just dump them on the table, then they're not in any particular order. It's just a heap. It's just a pile.
Exactly.
Of them.
It's just a heap of data.
Okay.
So all data is stored in what we call leaf nodes, and we'll reference this a couple of times when we look at the structures later on in this module.
Okay.
And a clustered index is really a good analogy that I'd like to think of is the contents page of a book. So you think you pick up a book and you look in the context page, that defines the actual order of the information within the book.
Okay.
So it's the physical ordering effectively of the order of the data within the book.
Okay, great.
Great. So if we then look at operations on clustered indexes, so first of all, we think about an insert. So you're inserting a new row. So it must, in order to maintain the order, it must be inserted into the correct position.
So if I'm just thinking about our book analogy, if that book were, let's say, my address book,
yeah,
and I meet a new contact and I want to keep their details, I'm going to go and find the page where, you know, the A's or the B's or whatever are, and I'm going to put their name in the right place. Okay.
Yeah, exactly. And we have this concept of splitting pages because we've got to put that into the right place. But, you know, with your address book analogy there, you've already filled the pages of Bolton because you know lots of Boltons.
Yeah.
And you need to insert me. You're going to have to insert a new page in there in order to do that data. And in SQL Server terms, what we would do is to split that page, and we'd have half the data on one, half the data on another.
Okay. I guess in Scotland it would be the M page because you got McDonald's and
yes,
all the rest of the
perfect.
M's. Okay, yeah.
Perfect. And then for an update operation, so the new, so when we do an update, we've got, if you're updating a row, it can either stay in the same place if it will fit,
okay.
But you may be updating data. So we talked about variable length data types before, where we had a varchar 50, and maybe you store 3 characters in there, and everything fits nicely within a data page within SQL Server, and you update that to have 50 characters, and then there's not enough space to store that on that page, so that again causes a page split.
Over. So, and I guess back to my address book analogy, if I've got a friend who changes their cell phone number, well, I just go and replace one cell phone number with the other and it stays on the same page.
Yes.
If they add a second house or a second address, there may not be enough room on that page and it might spill over. And of course, if it's a friend of mine who's a friend who's a girl who gets married, her name changes, that might mean, well, the thing I've ordered it in has changed, so I might have to move her to
exactly.
Okay.
Exactly. And then if we're issuing a delete operation, so basically we're going to flag the data as unused, so it's a less expensive operation. And then finally, select. So queries relating to the clustering key, so this is the order of the data that we're doing. So we can have a seek, and we can have a scan. So there are 2 types of operations on indexes, the seeks and scans, and we'll look a bit more at those when we come to the demos.
Okay, good to know.
Which is now, actually.
Oh, speaking of which, yeah, there we go.
Great. Okay, so first of all, I'm just going to use TempDB as a store rather than temporary tables. So I'm going to create a table. So we've been through this in the first module, how to create a table, called phone log, which I've just created.
Yeah.
And what we're going to do is have a look at the execution plan. So I'm going to use this button up here to include the actual execution plan.
Okay.
Because I want to show you this tab here. We have a table scan.
So this is how SQL Server's optimizer has decided that's the best way for me to get there.
Yes.
Right, okay.
And it's not so much the best way as the only way, because what we've defined here, we don't have a primary key, we haven't created an index, so therefore what we've created is a heap.
Yeah. Okay.
And how SQL Server accesses a heap is as a table scan. Because it's unordered data,
right.
There's nothing else it can do but start at the top and read through till it finds what you're looking for. So I'll drop that table. Now I'm going to create the same table, but this time with a primary key specified.
Okay.
And as I've just mentioned, when you specify a primary key, in order to enforce that primary key, it creates a clustered index.
Okay.
And this, because the table construct has changed from a heap to clustered index, we'll have a look at the difference that makes in the execution plan. So you see now we have a clustered index scan. So if you're ever looking at an execution plan and you see table scan, you know automatically that's a heap, because if there was a clustered index on it, it would be a clustered index scan.
I guess it's worth pointing out at this point that the clustered index was created because you specified one column as a primary key.
Correct.
Now, if I wanted to have a clustered index on a column that isn't the primary key, when I define the primary key, I'd have to explicitly say I want a non-clustered primary key.
Exactly, right. And then you would create a specific cluster.
Because we can only have one clustered index.
Exactly.
Yeah, okay.
So we can have a look in sysindexes here. So we can see the index has been aligned. So the same we were looking at foreign keys in the previous module, it's automatically generated a clustered index based on the primary key with a funny name.
Okay.
And it's also listed as a constraint.
So that constraint, there's a relationship between the fact it's a primary key and it has an associated index. That's what makes it a primary key.
Yes, yeah, exactly. So within that demo, so what we've seen here is the difference between a heap and a clustered index. There's a very kind of light intro into it.
Okay.
But if we switch back to the slides now,
okay,
and hopefully it'll all start coming together nicely. So the next thing that I wanted to talk about is non-clustered indexes.
Okay.
So we talked about table structured as a heap or a clustered index.
Right.
So it's one or the other, it has to be one or the other. And a heap within SQL Server is referenced as an index ID of 0, and a clustered index has an index ID of 1. So if you're looking through sys.indexes view, we just had a little look at in the demo, and you see an index ID of 1, you know that that's automatically a clustered index.
Okay.
But we don't, just because we can only have one clustered index, we've now got this concept of non-clustered indexes, which we can have a lot more of. So we can have these additional indexes called non-clustered indexes, which will have an index ID of 2 and greater. They're separate objects to the table, where a clustered index is essentially the physical ordering of the table itself. The non-clustered index is a separate object to the table, so the data within the non-clustered index will be copied out and stored separately.
And I know it's just worth pointing this out. I've taught a lot of students who find this concept quite confusing. To a certain extent, a table is either a heap or a clustered index. I know we talk about creating an index on a table, but when you create a clustered index, really that then defines how that table is stored. So a table can be either a heap or it can be a clustered index, but then we can create additional non-clustered indexes on the same table. And quite often you'll hear people talking about querying a heap or querying a clustered index. Really what they're saying is querying that table that happens to be physically implemented as either a clustered index or a heap. So just can be a little confusing.
So, and where we talked about the concept of a clustered index, the analogy of the contents page of a book, if we take that analogy further, a non-clustered index is very similar to the index at the back of a book. So where if you wanted to know everything in a SQL Server book around indexing, you may look in the contents page for the indexing chapter, and then you would read from there. But if you wanted specifically to read about non-clustered indexes, you may flick to the back of the book, and in the back of the book it will have non-clustered indexes, and then it will have the page number for you to find the rest of that information. And that is the equivalent of this last bullet here, where the leaf level contains a pointer to the table where the rest of the columns can be found. So this is the page in the back of the book where you can find the rest of the information that you're looking for.
Okay.
So this next slide is whether the underlying table structure is a heap or a clustered index subtly changes the architecture of non-clustered indexes. So in this example of a non-clustered index on a heap, this going back to that analogy of a book again, the index at the back of the book where we find the word that we're looking for on the page where we can find the rest of the information, that page number is what we call a row identifier, or a RID is how we reference rows in a heap. So in this diagram, the leaf node of the non-clustered index will contain a RID which points to a specific row on a heap.
So that's pointing me down, effectively in the non-clustered index, it's pointing me directly to that's where that row that you're looking for is physically stored.
Exactly.
Okay.
So where you can find the rest of the information. So where we have a non-clustered index on top of a clustered index, because the table structure itself is different, this row where we had this RID or this row identifier which sends us directly to the heap, when we have a clustered index underneath the structure, what we have at the leaf level of the non-clustered index is the clustered index key. So and then we'll go down, we're traversing the non-clustered index to find the clustered index key, and then we're going to go directly to the clustered index to find the rest of the information that we're looking for.
So just to kind of bring that into an example context, I guess if you have a table that has, let's say, a table of customers. So we have a customer ID, and perhaps we have a clustered index on the ID. So that's the order that the data is physically stored in. I may have a non-clustered index on last name. So what I'll do is look up the non-clustered index to find last name Malcom.
Yeah.
That then points me to the clustered index page where
you can get the rest of the data.
I can get the rest of the data.
Select statement. Yeah.
Okay.
So the next part is around covering indexes, and this is all related, and we should bring this together in the demo and right after this slide. So a covering index is an index that provides all of the data without having to go down to the underlying table structure. So we're talking about non-clustered indexes and clustered indexes here. So in Malcolm's example of customer ID, if I did a select first name and last name where last name equals Malcom, then the way that SQL Server would deal with that is to first of all have a look for a non-clustered index on surname, and we'll get down to, right, we've got the surname of Malcom, and then we've got this clustered index key, so we're going to go to the clustered index to get the first name column because it's not a part of the index.
Okay.
So if we had an index on last name and first name, it's what we would call a covering index, and this is how we would remove these lookups into the underlying table structure. Historically, we'd have quite wide indexes, but with 2005, we had this include option, which is really quite powerful for removing these lookups without the overhead of having a very wide index key.
So to be, again, just to be clear, the the kind of older approach, if you like, the only option we had before 2005 was the index then has to include multiple columns in the index itself. So I'm indexing on first and last name. Whereas the include clause lets me say, well, look, the index, the pages in the index where I'm storing the index value, it's just the first name. That's the only thing I'm indexing on. But when I get to the leaf node of that, include the last name.
Exactly.
So I then don't do the additional lookup to go and find that.
So we're copying the data, but we don't have the overhead of also sorting it by last name if we'd included it in the index key.
Okay.
So let's have a look at a demo of that now. So in this demo, I'm going to start off creating a table called book with a primary key. Then I'm going to create a non-clustered index. So notice the syntax here. So create non-clustered index. I'm going to call it IX book publisher, and I'm going to include publisher ID and the release date in descending order.
Okay.
Then I've got a query here to select a few columns from the book table where the release date is less than a year.
Less than a year ago, okay.
Less than a year ago. And I'm going to order it by publisher ID and release date. But before I execute that, what I wanted to show you was this estimated execution plan.
Okay.
So if we have a look at this execution plan, so this is how SQL Server will probably execute this based on the code that you've written.
Okay.
So we're going to do an index scan here, so non-clustered index. If we can have a look, we've got the output list from this index is the ISBN and the publisher ID. ISBN, release date, and publisher ID.
Okay.
Because we have a primary key on ISBN, which has created a clustered index on ISBN.
Okay.
And what I'm asking for is publisher ID, title ID, and release date. So within this non-clustered index key on publisher ID and release date, I have those values at the leaf level of the non-clustered index.
So I've got the ISBN in the clustered index, and I've got the release date and the publisher ID in the non-clustered index.
Yeah.
Okay.
So this primary key, so the clustered index key, exists in all non-clustered indexes. So if I'm asking for the ISBN and what do we have here? The publisher ID and release date, that would be a covering index.
Okay.
But because I'm asking for the title as well, I don't have that within the non-clustered index.
Right.
So what I'm going to have to do is to take this clustered index key, so the ISBN number, and I'm going to have to look it up on the clustered index.
So I get it from the leaf page of the non-clustered index, because that's ultimately what you find with a non-clustered index, is the clustering key if there's a clustered index.
Yeah.
And then I'm going and looking up through the clustered index to get the title.
Correct.
Gotcha.
Yeah. So I've got 2 out of 3 of the columns, the data columns that I need, and in order to get the title, I'm going to use the ISBN number to go and look up. And we can see at the bottom here, the output list from this key lookup is the title column.
Right.
So we have this index scan, then we've got a nested loop, because we're going to do a key lookup into the clustered index in order to fulfill this query.
And it's a loop because it's doing it for each key that it finds, because there might be multiple books that were published. Yeah.
Exactly. So, and this is fine and it works, and there's a 50% cost associated with both of these events. Okay. And that's how SQL Server worked, basically. But whenever we see key lookups, we're trying to remove them because they're quite expensive, and we've always got this trade-up of removing the key lookup versus having a wide clustered index. But in an example like this, we don't have to, because what I can do is create a new index on publisher ID and release date descending. So I've got the same cost, because
index, yeah.
I'm ordering by the same things, but this time I'm going to include the title column within this index. So when we get to the leaf level of the non-clustered index, and the optimizer will say now I need to go and find title from clustered index. Oh no, I don't, because it's already included in the bottom here. I'll just take this value and I'm complete.
So the leaf level, then, again, just to make sure we're clear on this, the leaf level of that non-clustered index is going to include the publisher ID and the release date. They're included on all of the pages in that non-clustered index, because that's what we're indexing on. When I get to the leaf, the thing I'm ultimately trying to find that I'm looking up, it's going to have ISBN because that's the key from the clustered index, and that's what's used to go and look up that. But now I'm also going to include the title down there as well. So I'm shortcutting any need to go any further because everything I need is actually at the leaf level of the non-clustered index.
Yeah, exactly. And it's quite lightweight. The only overhead really is the additional storage space, but it's much better that that's the only overhead rather than you're actually sorting by in order to have a covering index before, you had to have it as part of the index, even if you weren't worried about the order in which it was stored. So it's a great way of having that additional data just sat at the end of the index for you.
And when you say store, we're talking about the index pages, not the data pages for the table, but the pages that store the data for the non-clustered index.
Yeah, because the non-clustered index is a separate object, separate from the table itself.
Okay.
So I'm going to run the exact same query again, or I'm going to have a look at the execution plan for it, and you can see now that we have an index scan without the lookup. And the output list from this is the ISBN, because that's the primary key for the clustered index anyway, but we don't need to use that to do a lookup because we've got the title, the release date and the publisher ID all sat within that non-clustered index key. So we don't need to go to the underlying table structure to provide the data for that query.
So I guess one of the things this is kind of driving home for me is if you're implementing a database, to get this right, you've got to have a good idea what are the kinds of queries that I'm going to have. What are the most commonly filtered on columns going to be, because those are the ones that I'm going to be concerned about including in indexes. Yeah,
it's always a trade-off, and you can find if you're inheriting a database that there's always a trade-off between too many indexes and too few indexes. So there's an art to finding the right balance between too many indexes, too many include columns. You could be tempted to create an index and include all the columns, but then you're effectively duplicating the whole table structure itself. So there's a fine balance between.
And of course, every time you insert or update, you're going to have to move everything around to accommodate it. So
yeah, exactly.
Okay.
So if we just have a look at finally we just have a look at the AdventureWorks database here. We have a look at index columns within AdventureWorks. So you can see we've actually got a column here called isIncluded column.
Right.
So within the index columns, we can see whether it's been included or not.
I see. Okay.
So we can combine several of these system views to locate any included columns within the database. So within AdventureWorks, we weren't using AdventureWorks during that previous part of the demo. So this is me running the query against a different database, and it's showing me here that I have 2 indexes with included columns. So this first one here is a clustered index, so of course it's going to be included. But this second one here, the column name of comments, is an included column within this product review, product ID column.
Oh, okay.
And you don't need to remember, I mean, who's going to remember that query? You can also view this through Object Explorer. Let's have a look. We have a look at the production product review table. Under indexes, I can double click this and have a look here, and we can see this included columns tab here, so I can view the same information through the UI.
And of course you can create and manage them through the UI.
Exactly,
Yeah.
exactly.
Brilliant, okay.
Great.
Well, let's go back to the slides. So we looked at some system views there. I'm guessing there are other ways that I want to manage the indexes and see what's going on with them. Can you talk me through some of the DMVs?
Yeah, absolutely. So these are really important for everyday use as well as for the context of the exam, is to understand some of these key DMVs. So this first one here is DMDB index physical stats. So this will show you details around the size of the index and the fragmentation statistics. So when we talk about index maintenance later on, we will use this DMV to have a look at the fragmentation levels for an index. And fragmentation occurs as we're doing updates and inserts, and we talked about how those how we were managing those rows in the clustered index earlier in the module.
Okay.
And the next one is operational stats. So this is going to provide us with index and table I/O statistics. So how the volume of reads and writes happening on this table. And index usage stats is around usage statistics by access type. So when we have a look at the demo shortly, we'll see this kind of breakdown of these types of DMVs and where we can use that effectively for managing an environment.
Okay. Well, and now's your chance. Let's switch back to the demo machine.
Okay, so we'll start off by resetting our demo environment, create a new database. I'm going to create a copy of the phone log table that we've been using previously. I'm going to add a non-clustered index to this for reporting later on.
And of course, there will be a clustered index because there's a primary key that...
Exactly,
yeah. Okay.
Exactly. And then we're just going to insert some data into the table. So the contents of this query isn't important. It's just the fact that I'm pushing a load of data into the table.
Okay.
Then we're going to be using this DMDB index physical stats DMV. It's actually a dynamic management function to return details around the physical statistics. So you'll notice that we've actually got two entries for...
Yeah, I was going to say, I thought you said earlier I can only have one clustered index.
I did.
Okay.
So because of the way that the indexes work, remember we talked about root pages and intermediate pages and leaf level pages. Okay. So what we have within this clustered index here is an index level of 0, which is the leaf level pages, and index level 1 is actually the root page. So the highest index level is the root page.
So it's showing me the fragmentation, not just for the index as a whole, but for each individual level of the
Correct,
index. Okay.
Yeah. But most of the time what we're interested in is the leaf level fragmentation. So in this example, we have an average fragmentation of 7% at the leaf level of the clustered index, and a fragmentation of 21% on the non-clustered index that I created.
So what does that mean when you say it's fragmented? What?
So essentially it's, remember when we looked at the clustered index and we talked about these inserts and update operations that you do, when you have to, everything's in perfect order and then you need to insert data halfway up.
Sure.
We need to do this page splits.
So we're back to my McDonald's page being full.
Exactly,
and
exactly.
Okay.
So what you end up with is this kind of C page 47 to carry on and then get back there, so you end up with a lot of...
follow the leader to find the page.
Yeah,
right.
exactly. So this is the kind of fragmentation that we're talking about here. And the other point of interest is the page count, first of all. So a page within SQL Server is the storage unit within SQL Server, which is 8K. And we have an average page space used in percent. So it's 99% used. So what that's telling me is my pages are pretty well full. So I don't really have much fragmentation here. So I'm not too worried about this.
Okay.
And again, for the non-clustered index, I've got a low percentage there, but the pages are, I've got a relatively high, actually, fragmentation considering the work that we've done, but the average page space used in percent is quite high. Okay. So I'm not overly worried about this. So what I'm going to do here is do some modification, so that this is going to shuffle the data around.
Okay.
And hopefully generate some fragmentation.
So this is me updating my address book, changing people's telephone numbers or adding addresses or whatever it might be. Yeah.
There's been a mass migration of people in your address book.
Oh, people who know me constantly move without telling me where they've moved to. I can't understand why.
So we'll have a look at this DMV again, and what you'll see is for this leaf level page, we've now got fragmentation of 90%. So we've got 65% full for a page.
Oh, and many more pages as well.
Yes, exactly. So we've done some inserts, we've done some updates, we've got lots of splits. So the storage required for this this table is larger than it could be because we're 65% space efficient, effectively.
Okay.
So we're going to deal with how to remove that fragmentation in the next demo. But the next thing that I wanted to talk about was, remember this index operational stats that I mentioned on the last slide. So this provides you information around the usage. So this is a raw view of this data here. So what it is giving us here is inserts, so leaf insert counts, leaf deletes, and leaf updates. So this is the index being maintained.
So this is effectively a log of the things that have happened to affect that index.
Yeah, so it's how the index is being used. And if we have a look over here, somewhere we've got singleton lookups and range scans. So if you think about the purpose of an index is to increase the performance of accessing data within the underlying table effectively. So if an index it exists to be read from, but in order to maintain the right view of the underlying data, it needs to be updated. But whenever we're updating an index, it's kind of overhead in order to provide a later view presented by the index.
Okay.
That's all in this episode. I hope this tutorial was helpful. In the next episode, we will cover the remaining part of this topic, implementing indexes. Is your mind ringing with questions, queries, or doubt? Do you wish to learn more? Then visit our website www.millionlights.org and post your questions on our forum. We will be really happy to clear all your doubts. If you missed anything and want to rewatch it, you can download it from our website or can watch online as well. You can also participate in our webinars, discussion with the subject expert, as well as get Microsoft certification on various courses through our website. You can also find us on Facebook by the name Millionlights and also on Twitter. For more such interesting tutorials on coding, app development, programming, and building rich UIs, keep watching Microsoft Hour of Code, brought to you by Millionlights. Thank you.